Hey guys, welcome back. So this is part two of this week's lessons, I guess. So this is radar. So this is a time you will want to check out your PowerPoint real fast because I've got a couple of pictures up there. The first one is what exactly a radar looks like. And it is pretty much a gigantic soccer ball set on top of maybe some stairs or a concrete platform or maybe a building. And then the next picture is what it looks like inside. And inside is a big kind of antenna dish which rotates 360 degrees. And not only does it rotate, but it also tilts. So it'll shoot a beam out 360 degrees, then it'll tilt up. 360 degrees, tilt up, 360 degrees, tilt up. So it will continue to do that, and then it'll come back down. Now, depending on what type of mode the radar is in, and we'll talk about that in a second maybe, depends on how many times it tilts before it comes back down and starts over again. So a little bit of history first on radars, and I mentioned this couple of weeks ago during, I think, our very first class. But during World War II, military radar operators first began noticing returns on their radars from snow and also rain while they were busy looking for enemy aircraft. So after the war, it was like, what do we do with all these radars? So a lot of them were repurposed for weather. However, at the time, they could really only see the location of a storm and a little bit of the intensity. And even that wasn't all that great. You know, we look at radars today and we've got colors from blues and greens to yellows and reds and even blacks and whites. If you see white on a radar, run. That's a very bad situation. But back in the day, all you had was black and white. That was it. So seeing the intensity of a storm was pretty hard to do, but you could at least see the location. Really the first time that a weather radar was used on television was in 1961 when Hurricane Carla was approaching the Texas coast and around the Galveston area. So the story kind of goes at that time, Dan Rather, who really wasn't Dan Rather at that point, rather he was just a local reporter, he figured this radar was going to be a really big deal. So he went to the National Weather Service office, had them draw kind of a map of the Gulf of Mexico, and then overlay a computer image on top of that. It was a clear like plastic that they drew the map of the Gulf of Mexico on, a computer image of the radar and what the radar was seeing and just how big of a storm that was, how big Carla was. So that actually led to the evacuation of about 350,000 people out of the region. It was the largest evacuation at the time, but it saved thousands of lives because all of a sudden we had this new technology, not necessarily new, but at least new in a different way. Only 46 people died as compared to back in the year 1900. There was a hurricane that hit Galveston that killed in between 6,000 and 12,000 people. They'll never really know how many people were killed in that storm, but there was no advance warning, no knowledge of how big it was. Meanwhile, in 1961, Dan Rather kind of showed that to people, that this is how big this storm is, and that's also kind of how he became Dan Rather and set on his path a little bit later on. Today, there are 160 Doppler radars which are operated throughout the National Weather Service office. Again, check out your PowerPoint. You will see dots representing all of those radar locations. Here in Louisiana, we have one in Slidell. There's one in Lake Charles, and then there's also one up in over towards the bases over in Vernon Parish as well. These are all known as what are called WSR 88Ds. They were put into operation around the year 1988, so they are getting a little long in the tooth. However, the next generation of radars is beginning to be developed, and that D stands for Doppler, and I'll tell you what makes a Doppler radar in just a few more minutes. Also, check out the next slide, and you kind of see the coverage from those radars. You'll notice that there are actually some gaps out towards the west. There's better coverage and more overlapping coverage from the central portion of the country towards the eastern half. A couple of reasons for that. One, there are more people in that area. Two, that part of the country, the central and the eastern portions, see more severe weather, more tornadic outbreaks, more hurricanes, and have more of a need of radars. So also out towards the west, there's some areas that are completely unpopulated in places of Wyoming and New Mexico and Arizona and Nevada. So there are fewer people in those regions, so you don't need quite as much coverage. Also, they don't see the severe weather that we do across the Central Plains and especially the Southeast and then going into the Northeast as well. So a little bit more coverage on our radar maps from the central portion of the U.S. moving towards the eastern portion as well. So I mentioned what makes a Doppler radar a Doppler radar. Well, it's what's called a phase shift, PHASE shift. So I'm kind of draw this out for y'all here, just kind of forgive me. So here's your radar right there, kind of hard to see, but there's your radar, and it's going to shoot a beam of energy out. And let's say this is our thunderstorm over here, okay? So as this beam of energy goes out, it goes out at a very specific frequency. From here to there is a frequency. So as that radar beam of energy hits this thunderstorm over here, some of it is refracted, some of it is absorbed by the raindrops that are within here, but some of it gets reflected back towards the radar. So it comes back at a different frequency. So frequency from here to there is different from this frequency up here. So the radar knows, okay, well, I sent it out as one frequency and it came back as a different frequency. So then I know if that raindrop or what I hit is moving away from me or moving towards me, because this is not moving anywhere. It's at a stationary location. Meanwhile, this is what's moving. So it knows whether it's moving away or towards it. So kind of think of it like this. Think of it like you're standing on a train track and you're standing in one spot, okay? There's a train that's coming at you down the tracks. Please don't stand on the tracks, just next to the tracks. So as it's coming down the tracks and you hear the whistle blowing, it changes frequency, it changes pitch as it gets closer to you. Then as that train moves further away from you as it passes by, it's going to change again. You're in one stationary spot. However, the frequency of that sound is changing as it gets closer to you and as it moves further away from you. So it's kind of the same thing. So it sends it out at one frequency, but it comes back at a different frequency. So it knows if that storm is moving away from it or if it's moving towards it. So just a little different. So that's kind of how it sees into a storm. So if you ever see on television, this is a Doppler radar indicated tornado, that's what it's talking about. We'll talk more about that in a second. Radars are great. Obviously, we see where the rain is falling, where it's headed towards. However, there are a couple of problems with radars. One is beam spreading. So, again, you have your radar, and here's your thunderstorm over here, okay? So as this beam shoots out, it gets wider and wider as it shoots towards the target. Beam is only good for about 100 miles. After that, that beam is too wide. So as it hits this thunderstorm, it may be a really strong thunderstorm with a really strong core right there in the center, but the beam is so wide and so weak at that point that it underestimates how strong that storm is. So that's one problem. Another one is beam height. So, as we know, the Earth is round, yes. So here's our radar. Here's our thunderstorm over here. As this beam shoots out, it's going to gain height just because it's going away from the surface of the Earth. The surface of the Earth is tilting away underneath it, so the beam is just going to get higher on its own. Even if it's going out straight, it's going to gain altitude because the Earth is falling away from it. So it's going to be going a little bit higher than what it wants. So let's say the core of the storm is down here. It may completely overshoot the worst part of that storm, therefore saying it's not as bad as it looks like it is because it's actually missing the core of the storm. So that's another problem with radars. Another one is the cone of silence. I mentioned how radars, how the antenna inside will tilt. Well, it can't tilt straight up. So it can't see exactly what's going on directly overhead. So that's what's called the cone of silence. Sometimes you'll see a whole bunch of weather, a whole bunch of rain, heavy rain all around the radar, but there'll be a little black hole right in the middle. It can't see directly above it. So sometimes as meteorologists, if you're watching severe storms come in, you may have to switch radars because that one radar is being directly affected by the storm and is kind of unusable at that moment. And then it just takes time to receive the images. You know, by the time the radar beam shoots out, comes back, computer analyzes it, sends it to the National Weather Service, you get it as a meteorologist. A couple of minutes have passed. So you may be saying, hey, this storm is approaching Alexandria, but probably it's a little bit closer than what it was when you're showing it on TV, just because of the time elapsed. So there is some time there as well. Hopefully we'll get that down with technology. Actually, I'm going to stop this right here. I'm going to come back in just a minute and talk about the radar product. So hang on, be right back.